All right, welcome to lesson 3 here. Today we're going to be looking at what's called the trapezoidal sum method. So rather than using rectangles, we're going to talk about using some other shapes to more closely approximate the area under a curve. So we looked at this same scenario here the other day where we were using both the left-hand sum, the right-hand sum, and midpoint methods, but today we're going to be looking at another method. So again, this is Jada's velocity given by the function v of t equals t squared, and looking from 0 to 10 hours. And again, we approximated this. So question number 1, what are the advantages and disadvantages of using rectangles to approximate area, right? What are the advantages? What are the disadvantages? One, advantages, rectangles are super easy to calculate the area. So easy to calculate area, right? It's just base times height. Bam, done. Disadvantages, though, and these are very important, right? Why is a disadvantage? Consistently, we will get under or over estimates. Consistent over or under approximations. Not very accurate, right? That's kind of the big disadvantage. It's close, but we can just see, right? Even if we just use this interval right here from 0 to 3, that's not a very good approximation of the area under the curve. The area under the curve is this part right here, right? Just this part here. What is all this? All that is error. It's not great, right? Well, okay, fine. Say, all right, well, we can get rid of a lot of that error. We can. We can, right? We could use a midpoint approximation. That would get rid of a decent amount of that error, because in this situation, we have both an underestimate and an overestimate, and they're kind of offsetting each other, right? That's one way we can get rid of that. Another way we can get rid of that is we can use smaller intervals, right? Let's just say we break this up into, like, I don't know, 4 different intervals and do it this way, right? Now this is pretty good, but now we're kind of taking away the easy to calculate part, right? Now we're calculating a ton of intervals, even though it's much closer to the actual area. So there's always drawbacks here, right? You can increase the number of intervals, you can use midpoints, you can do all these things, but none of them really fix the problem. So question number 2 says, what if we use a trapezoid? And so what does that look like, right? So that looks like this. We find the height at the beginning and the end of our interval, and then in between that, we just draw a line, and that's our shape. Now, that's a pretty good approximation. And this side right here, that's our base 1, that's our base 2, and then over here, this interval width, that's our height. And we have a pretty good approximation by changing the shape from a rectangle to a trapezoid. So if we use trapezoids instead of rectangles, what's this going to do to our approximation? Well, it's going to make it better, right? It's going to make the approximation better. It will make the approximation better because the trapezoid fits the area beneath the curve better. Pretty simple, right? This fits the area under the curve better. So this is going to be a better approximation. Alrighty, let's go ahead and keep moving on. Question 3, use 10 trapezoids of equal subintervals to approximate Jada's distance. Sketch these trapezoids on the graph. Okay, so we already got some of these on there, or one of these on here. So I'm going to kind of use that. Maybe not. I'm going to just use lines to make this work. So here's one of them. I am somehow not doing a good job here. Undo that and go to the line tool again. Okay, cool. This should be better now. So here's our interval that we had before. Kind of keep adding to that. Again, what we're doing here is we're just trying to show how good the trapezoid method is in comparison, right? I'm not trying to make these exact or perfect or anything, but I just want to kind of show how good of an approximation the trapezoid method really gives you, because it's pretty good compared to the rectangles. And I'll just connect these tops. And notice how the tops of these are pretty much following the graph. I mean, it's not perfect. There's a slight over or underestimate in certain places, but it's pretty good. And we didn't have to increase the number of intervals at all. We just had to kind of change the shape we were dealing with, right? So here are our intervals. The only thing that's going to make this a little bit harder is the area formula for our trapezoid, right? Area formula for the trapezoid is a little bit harder to calculate. It's base 1 plus base 2 divided by 2 times height. And so these trapezoids, remember trapezoid is a shape with parallel sides, and then these are our bases. These trapezoids are turned on their side, right? They look a little different than this. One of our sides is flat. That's our H there. And these are our base 1 and our base 2, and these are turned on their side, right? So the height of our trapezoid is actually the width of our intervals. And the base 1 and base 2, well, that's just the left-hand and right-hand side that we would use for our normal rectangular Riemann sum approximations. So not a lot different going on there. So let's go ahead and go through how we would calculate these. So for our first interval there, again, they all have a width of 1. So when I write this out, it's always going to be times 1. I'm not going to write that over and over again. I'm just going to kind of do the other one. So it's going to be 1 times 0. That's the height of this side here, plus 1 squared, right? 1 squared, which is 1. I won't even write both parts. I'll just plus 1 divided by 2 plus 1 times, and I'm not going to write that 1 times each time because that's it's a little tedious, but it's something I want to keep in mind. The width of our interval is always 1, and it is technically involved in this calculation. Now, the height of this side here is going to be 1 plus the height here is 2 squared, which is 4, plus, and then we move on. This one's going to be 2 squared plus 3 squared. That is again corresponding to this rectangle or this trapezoid right here. 2 squared, 3 squared divided by 2. And again, just pointing out everything here is sort of getting multiplied by 1. Actually, I can just use some brackets to indicate that. Plus, and now it's going to be 3 squared plus 4 squared divided by 2 plus 4 squared. Oops. We'll do it this way. So plus 4 squared plus 5 squared divided by 2 plus 5 squared plus 6 squared divided by 2 plus 6 squared plus 7 squared divided by 2 plus, and you can kind of get the idea here, right? This is our first trapezoid, second trapezoid, third, fourth, fifth, sixth, seventh one. So let's look at that seventh one here. So 1, 2, 3, 4, 5, 6, 7. That's this one right here. Its left side base, or the height here, is 6 squared. Again, the reason I'm squaring these numbers is because it goes back to the original function, right? At 6, this has a function value of 6 squared, 36. And then at 7, it has a function value of 7 squared, 49. Right, so those are our bases, and then our height being 1. Okay, and then moving on, we should have a few more intervals to try to do this with. 49 plus 8 squared, 64 over 2, plus 64 plus 81 over 2. And then finally, I think this is our last one, 81 plus 100 over 2. Okay. And again, all that's being multiplied by 1, which would be the width of our interval, or you could kind of distribute it in and multiply by all these, but whew, a lot of calculating there. Okay, so I'm not going to subject you to me typing this all in. I've already done this calculation here on the side. It is 335. Keep in mind that we are dealing with kilometers. This would be a measurement in kilometers. So what does this mean? This is a very good approximation of the area under the curve using trapezoids. And that area is the area under this curve, the true area under this curve is very, very close to 335. In fact, if we do a little bit of Desmos here, I'm going to just sort of give away some stuff that Desmos can do. So let me get rid of this here. Let me type in an equation y equals x squared. And let's make sure that we can see all the way to 100 there. So I'm going to change my y-axis, which make that go up there. Okay, so scaling, a little different than what you can see, but we're looking at the, y equals x squared, which is the same graph that Jada's is, it's v of t equals t squared, but basically the same idea. I want to calculate the area under this curve from 0 to 10. So this is going to be some notation that you aren't familiar with, but the integral from 0 to 10 of x squared dx. This is the notation that you should use with this. This is the area under the x squared graph from 0 to 10, 333. That is the exact answer of the area under this curve from 0 to 10, 333. And you can see that our calculation, boy, you weren't seeing that, were you? So let me undo this real quick. Let me just show the graph again. Cool. So now you can see what I typed in. So the integral from 0 to 10 of x squared dx. This is the area under the curve of x squared from 0 to 10. It's calculating this area for me, 333.3 repeating. That's the exact area under this graph from 0 to 10. You can sort of see it and shade it in here, and that didn't really work well. Anyway, so hide that, transition back, cool. The answer we got, pretty darn close. If you remember the other day, we did some estimates, and those were farther off. They weren't quite as good as that approximation. Cool. So how does your answer in question 3 compare to your LRM and RRAM results from yesterday? Much closer to the right answer, basically, right? But more specifically, this is actually an exact average of the LRM and RRAM. So this is the average of the LRAM and RRAM from yesterday. Exact average. Let me go ahead and pull up those exact numbers just so that I can remember what those were. So the LRAM calculation we did yesterday was 285. So we did an LRAM yesterday, and it was 285. And for some reason, I can't seem to find the RRAM that we did, but let's kind of quickly look at that, right? What would that look like? We can do it, right? It's not so bad. So that would be this rectangle here, located at 1. So that would be 1 squared, which is 1 times 1, which is our width. Then we have another width of 1 and 2 squared, so that'd be plus 4, plus 9, plus 16, plus 25, because again, that's the height, 25 times 1, plus this one's 36, 36 times 1, yeah, 36. This one would be 49, 64, 81, and then 100. Again, quick calculation here. And so let me just go ahead and add those all up just to get a RRAM calculation. Okay, and so doing that, I got a quick calculation here of 385. That was my RRAM calculation, so the right hand Riemann approximation. 385. And if we average those two values, so to average something, you add them together, and then divide by 2. Quickly, I'll do that. 285 plus 385 is 670. 670 divided by 2 is 335. So that equals 335, which again is what we came up with. Why? Why is that the case? That's because this is an average right here. This is an average. So if we take a look at one of our rectangles again, let's say we look at this one right here. This is one we looked at earlier, and I say rectangle, I mean trapezoid. So B1 is the left hand of our interval. So that's the value we'd be using if we did a left hand Riemann approximation. B2, that's on the right hand side, right over here. This is our right hand height. And we're averaging those, right? We're adding them together, we're dividing by 2. So we are averaging the left hand Riemann height and the right hand Riemann height, and then we are multiplying by the width of the interval. So baked into the calculation of the area of this trapezoid is an averaging of our left and right hand heights. That's why we get an average there. Cool. Let's go ahead and go to the summary page here. So some important ideas. Area of a trapezoid is equal to this calculation right here. That is averaging our left-hand side and our right-hand side heights of this. And then the height in the area of a trapezoid actually refers to the width of our intervals, right? So the area under the curve is pretty close, right? It's approximately equal to the sum of all of these trapezoids. So however many trapezoids we want, obviously just like rectangles, the more of them we do, kind of the better an approximation we have. You can see here with this graph, as it curves up and down quite a bit and we don't have that many intervals, you can see that there is a good amount of over and under approximation that is happening even with trapezoids. And then finally, the trapezoidal sum, which we just kind of worked on there, is the average of the LRM and RRM values. So you can directly calculate the trapezoidal sum, or you can calculate the LRM and RAM values and average those. Either way, you can find the trapezoidal sum. Anyway, see you guys next time.